In this video, we're going to look at the Taylor and Maclaurin series. We're going to be able to describe the procedure for finding a Taylor polynomial of a given order of a function. We'll be able to explain the meaning and significance of the Taylor theorem with the remainder. We're going to estimate the remainder of a Taylor series approximation of a given function. Now, we're going to discuss which functions can be represented by power series and how to find those representations. And then we're going to also talk about finding a power series representation for a particular function and whether or not that series converges. And then proving it actually does converge. So let's start first by looking at a not convergent type of series. So consider a power series that is centered at A. Then this is what it would look like when we expand it out. If x does equal a, we just get our original c naught, which means f of a equals c naught. Now, assuming that it doesn't equal a, because, that's boring. Assuming it doesn't equal a, then we'd take the derivative of our series, which we know from the last section. We can do it term by term, and this is what we get. And if f prime of a equals c1, then we continue along this process until we get the Taylor series, which is, we have our function f of n of a, of n factorial over x minus a raised to the n, is going to be f of a, f being the center, or a being the center, so f of a would be the output when I put in that center value. F prime of a, x minus a, f double prime of a over 2 factorial, x minus a squared, and all the way down. This is, and then if my center equals 0, then we have the Maclaurin series. Now we know from the theorem 6.5 and 6.2 that this series this representation is unique, which gives us the next theorem. If a function f has a power series a that converges to f on some open interval containing a, then that power series is the Taylor series for f at that center a. If I want the nth partial sum of a Taylor series for a function at f at some a is known, and we call this the nth Taylor polynomial. So p naught, where we have f of a, this is the 0 degree. P1, I do the first two terms of the Taylor series, which is f of a, f prime of a, x minus a, p2, p3, and etc. If x equals a, then I have the Maclaurin series, Maclaurin polynomial. If f has n derivatives at x equals a, then the nth Taylor polynomial for a is p of n of x. So like the first, so degree 1, I'd have just the first one. Degree 2, I'd have the first two terms. Degree 3, I'd have the first three terms, and etc. The nth Taylor polynomial for f is known at 0 is known as the Maclaurin. So that's the difference between a Maclaurin and a Taylor. If we're asked to find the Taylor polynomial of degree 2 for the given functions centered at the given point. So here's our function, and here's where we're centered. We're centered at x equals a. Because I need or want a degree 2, I am going to need for each one of these, p of 2 of x is going to be equal to f of a plus f prime of a, x minus a, plus f double prime of a, x minus a, the quantity squared, all over 2 factorial. This is a Taylor polynomial of degree 2, and I know I have a degree 2 because I am at the second derivative, and that's when I stop. If I want degree 3, I'd stop at the third derivative. If I want degree 1, I'd stop at the first derivative. If I want a degree 0, then I'd just have f of a. So I need to find, these are the things I'm going to need to find to fulfill this, is I'm going to need to find f of a. So I need to find f of a, which is f of 1. And I put 1 in there, and I get 3 out. So 1 plus 1 plus 1, I get 3 out. I also need to find f prime of x evaluated at a. So first I'm going to find the derivative, which is going to give me 1 plus 2x. And then I also need f prime of a, which is f prime of 1, which is equal to 3. I will also need my second derivative of my function, which is just 2. And then, of course, it makes no sense to evaluate f double prime of 1 because it's only going to give me 2. Now I'm ready to follow this pattern. So p of 2 of x is equal to the f of a, which is 3, plus f prime of a. F prime of a was 3, and then x minus 1, and then plus, and then I have f double prime of a, which is 2, x minus 1, the quantity squared, all over 2 factorial, which is just going to be 3 plus 3, x minus 1, plus x minus 1, the quantity squared. Now here's the thing. I could, if I wanted to, multiply all this out and simplify. And if I were to multiply all this out and simplify, I would get this polynomial. Let's take a look at my next example. Again, I'm going to find the degree 2. So I will need f of a, which is f of pi halves. And f of pi halves is just going to be 2 sine, the sine of 2 times pi over 2, which is the sine of pi, which is 0. Cool. Then my second thing that I'm going to need is my derivative, so f prime of x, which is going to give me 2 the cosine of 2x. So then I need to evaluate at a, so f prime of pi over 2, which is going to give me 2 the cosine of 2 times pi over 2, which is pi, so I have negative 2. I'm going to need my second derivative, which is going to give me negative 4 the sine of 2x. And I also know that when I do any sine of 2 times pi over 2 will give me 0. So 5 f double prime of a is f double prime of pi over 2, which is just going to give me 0. So this Taylor polynomial of degree 2 is going to be equal to 0, and then plus I have negative 2 x minus pi over 2, and then plus, and then this one is 0. So it's 0 multiplied by the x minus pi over 2 squared over 2 factorial, but this is 0. So my final answer is negative 2 x minus pi over 2, and that's my answer. Okay, so the first one, with a little bit of factoring, I could have came up with this, uniquely come up with this. But this one is a little bit more interesting to try to come up with a Taylor polynomial from something like this. Let's take a look at my next example. So once again, I'm going to need my f of a, which is f of 1, which is 1. I'm going to need my first derivative, so f prime of x, which is going to give me negative 1 over x squared. F prime of 1 is going to give me negative 1. I need the next derivative, so f double prime of x, which is going to give me negative 2 over negative, so it's positive 2 over x cubed. F double prime of 1 is going to give me 2. So my p of 2 is going to give me 1 plus, I have negative 1, x minus 1, and then plus 2, x minus 1, the quantity squared, and then over 2 factorial, which is just going to give me 1 minus 1 x plus 1, minus 1, I don't know why I switched it to a plus, and then plus the x minus 1, the quantity squared. We would like to know whether or not our Taylor series that we're coming up with converges. And to do that, we would have to determine if the sequence of the Taylor polynomials p sub n converges. But what we really want to know is whether or not the sequence converges to f. To do this, we must define what the remainder is. The remainder is going to be defined as our original function minus our Taylor polynomial. When n equals 0, as an example, I have a remainder at the 0, which is f of x minus p naught of x, which is just f of x minus a. If f is differentiable on an open interval I, where a and x belong to I, the interval I, then the mean value theorem, this is from Calculus section 4.1 in our volume 1, there exists, this funky looking e, there exists a c in the interval from a to x such that f of x minus f of a will equal f prime of c times x minus a. So my remainder when n equals 0 is f prime of c x minus a. So then using the mean value theorem, again this is section 4.4 in your calculus book volume 1, we're going to get this as the remainder. R of n of x is equal to f raised to the n plus 1 c, n plus 1 factorial, n x minus a, n x minus a raised to the n plus 1. For some c in this interval, c being a real number. Now, further, if I take the absolute value of the derivative of the nth plus 1 derivative of x, it will be bounded by some m in this interval, and m is going to be a real number, and we get this for all x in the I. So, let f be a function that can be differentiated on n plus 1 times on an interval I containing the real number a. Let p sub n be the nth Taylor polynomial of f centered at a, and let my remainder be r sub n of x is equal to f of x minus p of n of x, be the nth remainder. Then for each x in the interval I, there must exist a real number c between a and x such that this holds true. And if there exists a number m such we are bounded from above for all x in I, then the absolute value of our remainder sub n must be less than or equal to my m, my bound, n plus 1 factorial multiplied by the absolute value of x minus a raised to the n plus 1 for all x in I. You would actually use MATLAB or Octave or one of the other programs that are out there for math that include approximations of functions to be able to do these remainders. Now, I don't require that because of where we are. When we're back in the classroom again, we will use some sort of software to go through these, but right now we don't have that option, so it's just there. I'm not going to ask you to do homework questions on it, and it's unfortunate that we won't be able to do more with it, but that's okay. We'll survive. Now, if we want to represent a function with a Taylor and Maclaurin series, we will now be beginning that discussion about convergence. To determine if it converges, then we're going to take the limit as n goes to infinity of our Taylor polynomial. Since the remainder of this function is f of x minus p sub n of x, the Taylor series converges to f if and only if the remainder is, as the limit as n goes to infinity, is equal to 0. Now, suppose that f has derivatives of all orders in the interval I containing a, then the Taylor series is this. And it converges to f on all x in I if and only if the remainder, the limit as n goes to infinity of r, my remainder is 0 for all x in I. So, find the Taylor series for the given function centered at the indicated point. And what this is asking me to do is I'm going to try to find a Taylor polynomial that is centered at -1, but I don't know, like the previous example, I wanted a Taylor polynomial of degree 2. This one I just want a Taylor polynomial, and I'm not given a degree. So what I'm going to do is, because my Taylor polynomials will require me to find f prime, f double prime, f triple prime, and etc., I'm going to start doing some derivatives and see where I am. So f prime of x is going to be 1 plus 2x plus 3x squared. F double prime of x is going to give me 2x plus 6x. And that's just 2 plus 6x. And f triple prime of x is going to give me just plus 6. And then I can't go any further. I also need some evaluations. So I'm going to do f of -1, so f of a, which is going to be 0. I'm going to do f prime of -1, which is going to be 2. F double prime of -1, which is -4. And f triple prime of -1, which is 6. So my p sub n of x is going to be equal to my f of a, which is 0, plus my f prime of a, which is 2. And I'm going to have x minus becomes plus 1, and then minus 4, x plus 1 squared over 2 factorial, plus 6 over x plus 1 cubed over 3 factorial, and etc. But everything after the third derivative is equal to 0. So then my final answer then is 2x plus 1 minus 2x plus 1 squared plus 2, actually 3 factorial is 6, so that's just going to be plus x plus 1, the quantity cubed. And that's my final answer. Now let's take a look at one in which we don't have the derivative end after so many derivatives. This one ended after the third derivative, the fourth one is 0, and so everything else beyond that just cancels. In this example, that's not going to happen. So I'm going to do f prime of x, which is the cosine of x. F double prime of x, which is negative sine of x. X triple prime of x is going to give me negative cosine of x. And the fourth derivative of x is going to give me back to positive sine of x. All right, so we kind of get a feeling for what this is looking like. So let's go ahead and do the evaluations. Of course, f of pi over 2 is equal to 1. F prime of pi over 2, which is the cosine, is going to be 0. F double prime of pi over 2 is going to be -1. F triple prime of pi over 2 is going to give me 0. The fourth derivative of pi over 2 is going to give me back to positive 1. So p sub n is equal to my f of a, which is 1, and then plus my f prime of a is going to go to 0. So even though I'd have the x minus pi over 2, it would go to 0. The next term, which is going to be -1, and then it's going to be x minus pi over 2 squared over 2 factorial. My next pi, the third derivative of my a, is going to go to 0. And what will happen is every other derivative will go to 0. Then this one is going to go back to positive 1, x minus pi over 2 raised to the 4th power over 4 factorial. So what I have is 1 minus x minus pi over 2 squared divided by 2 plus x minus pi over 2 raised to the 4th, 2 factorial, 4 factorial. Well, if I wrote this as 1 factorial, and not only did I do that, but I can also write this as 1, and then x minus pi over 2 raised to the 0. You can see the pattern here. The pattern is it's going to alternate. And I should actually do ... because this is going to continue. So dot, 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 dot is equal to n equals 0 to infinity of, it's alternating, -1 raised to the n. In my denominator, this is 1 factorial. This is 2 factorial, but I'm in when n equals 1. This is when n equals 2. So if n equals 1 and n equals 2, and this is n equals 0, so 0 times something is going to be 1, and I can rewrite 1 factorial as 0 factorial because they will have the same thing. So 0 factorial is equal to 1, 1 factorial is equal to 1. So with that said, then I know my denominator is going to be 2 times n factorial, and then I have x minus pi over 2. Now the powers are going from 0 to 4, so it must be 2 to the n. And that is my Taylor polynomial and written as a series. Let's take a look at my next example. So once again, this is something that's going to just keep repeating itself over and over again. So we kind of like it when that happens, and we kind of don't. F prime of x is e to the x. F double prime of x is still e to the x. And you're going to say, wait a minute, isn't this going to be e to the x all day long? And the answer is yes, this is e to the x all day long. That means when I put in my -1, so f of -1, each one of these I'm going to get 1 over e, and then I'm going to add all of these, because e raised to the -1 is 1 over e. All right? So then my p sub n is equal to my f of a, which is 1 over e, and then it's going to be plus 1 over e, 1 over e, and then x plus 1 plus 1 over e, x plus 1 squared over 2 factorial, plus 1 over e, x plus 1 cubed over 3 factorial, plus dot, dot, dot. So this is going to be equal to 1 over e, because it's going to be common in all of them. So I'm going to factor out the 1 over e, and then I'm left with 1 plus x plus 1 plus x plus 1 squared over 2 factorial. I could write this as 1 factorial. I can write this over 0 factorial. And at the same time, I could say, really, this is x plus 1 raised to the 0, just like it is 0 factorial. And then we start to see the pattern that this is going to be the summation of 1 over e. And I have 1 over n factorial, x plus 1 raised to the n. I'm just going to bring that e in, so I can write this as a summation of n equals 0 to infinity, n equals 0 to infinity, of 1 over e n factorial, x plus 1 raised to the n. So that's what my Taylor polynomial series will look like. Let's take a look at my, I believe, last example. Just want to confirm this is, I feel like this is my last example, but you never know with me. Pretty sketchy. Yeah, this is it. What? A video that's less than an hour long? What? Okay. Now this one's a little bit different. And the reason this one is a little bit different is because I have this rule, right? We have this rule that says if I have 1 over 1 minus y, 1 over 1 minus y, this is equal to the series as n goes to infinity, n from n equals 0, n equals 0 to infinity of y to the n. Now my goal, every time I'm doing this, is I'm trying to take something that is not a series and turn it into a series. Like, as an example, e to the x can be rewrote as this series if I'm centered at -1. So if I'm centered at -1, then this is my series. This can represent e to the x. So I'm trying to figure out what kind of series can represent this. So I see and I remember that the derivative d dx of 1 over 1 minus y is going to be negative, negative, so it becomes positive 1 over 1 minus y, the quantity squared. Now, if I do the second derivative, so d dy, and this is y, so I'm doing it generically, of 1 over 1 minus y, the quantity squared, then I'm going to get 2 over 1 minus y, the quantity cubed, which kind of looks like what I have. Now remember, if I'm doing the derivative of this side, then I'm going to do the derivative of this side. So I'm going to do the d dy of the summation of n equals 0 to infinity of y to the n. Now we know from Tuesday, when we did this, what we would do is we would expand this out. And what we find when we expand this out is we end up with this being equal to the summation of n equals 0 to infinity of n y to the n minus 1. And then I would do the second derivative of this. I'm going to do the derivative again. So d dy of the summation of n equals 0 to infinity of n y to the n minus 1. And we end up with the summation of n equals 0 to infinity of n minus 1 x raised to the n minus 2. Now, this is where I'm at. And this should be, yeah, that should be, check my derivative. Take the derivative of that, so bring the 2 down, and it's -2. Okay, so we're good there. All right, so 2 over 1 minus y raised to the third power is going to be equal to the summation of n equals 0 to infinity of n minus 1 raised to the y, the n minus 2. Now, that was in y. That's my goal. I took my rule, and I did derivatives twice. What I have, however, is I don't have y. What I have is I have 1 over x minus 1 raised to the third power. And I can rewrite this as 1 over -1 plus x raised to the third power, which I can rewrite this as 1 over -1 to the third power x, or 1 minus x to the third power by factoring out a negative and raising it to the correct power. So then this is equal to -1 over 1 minus x raised to the third power. So what that does for my goal here, it's going to make it a negative. So this is going to be a -2. So now I'm at -2 over 1 minus x, the quantity cubed, is equal to the summation of n equals 0 to infinity of n minus 1, x, now I'm in terms of x raised to the n minus 2. So 1 over 1 minus x raised to the third power is going to be equal to n equals 0 to infinity of n minus 1, and then I have x raised to the n minus 2 all over -2. Now this is pretty straightforward up into this point. Here's the deal. I cannot have negative exponents for this to be a polynomial. So for this to work out right, I need to shift this so that when I put in 0 in right here, I'm not going to get a negative number. So I need to shift this. The way I'm going to shift it is in here. So I still need to start out with 0, right? So if I start out with 0 right now, I'm going to get x raised to the -2. And I can't have that. So where do I start? Well, I need to start out with n. So in other words, I need to shift this entire thing over 2 places. So I can start at n. So this is going to be equal to the summation of n equals 0 to infinity of n plus 2, because I'm going to add 2 here, I'm going to add 2 here, and I'm going to add 2 here to shift it so that I can start at a positive exponent for my series, my power series. So then this is going to be n plus 1, x raised to the n, all over -2. And that's my final answer. And that's because the first couple of terms are junk. They're not a part of the polynomial, because the polynomials have degrees 0, 1, 2, 3. So I can't have negative exponents, nor can I have fractional exponents on my x. And so I had to do a shift. And that's it. That's it for this section. Nice, easy peasy, lemon squeezy.